Okay, good morning, guys. Let's get started. So last session we talked about the fundamentals of neural network, how we're gonna stack up several layers of classifiers. So those several layers could be either perceptron, or could be logistic regression, or could be any other nonlinearity in your activation function, so that you can apply a soft threshold towards your weights. And so we reach up to the point that we can, by using several layers, we can represent more sophisticated representation of nonlinear data, right? So this session we're going to talk about the forward pass, or what we call forward propagation, and this is defined as sending an input to your network and then get the output as the classification. So in the case of a convolutional neural network, this could be, your input could be the pixel of your images, your input images, and the output could be the classes that the network classified based on that input, right? In the case of neural network, this input could be anything, like a sequence, some other data, speech, or any other things. So today we're going to talk about forward pass, and on Monday, make sure you attend the class because we're going to have the formalization of backward pass. And this is going to help you in order to do your second assignment. All right, so as before, we define our input as x's. So 1, x, x1, x2, up to xt. So we have d-dimensional input. And so for all the layers in our network, so the layer L1 2 up to the capital L, we do the following. So we update the S of L, which is the current node, at layer L by the weight of L, so the vector L transpose, multiplied by the weight, by the input that was coming from the previous layer, right? So we have to do it in a loop for all the layers. And then afterward, we're going to have a new set of inputs from the application of the activation function. In this case, that theta could be sigmoid, or in neural network is hyperbolic tangent, or we have other nonlinear activations. So after you computed your current node, you have to compute the output of the node. That's going to be the input of the next node. And then the loop ends here. So in a high level, in a nutshell, you put the input, you compute the S of L based on the weights and the input, and then the output of that would be the input of the next node. All right? Now let's see what's going to be the computational complexity of this process, because we have to do many multiplication, we have to do many additions. And normally there's a metric in neural network, mostly in CNNs, they call it max, which represents the multiplication and the addition. So like when they say, for instance, AlexNet has like 20 million max, it represents the number of multiplication you had to do here, and then the addition with the biases and other things. So it is one of the metrics that you can represent how complex the number of computations are. All right? So in general, if you want to calculate the computational complexity, so first we have to define the total number of nodes. So we will define them by V. And they start 0 up to L, right? and the total number of edges. So those edges that connect your V's here. So you have like this, and these are the edges that connect them, right? So all of them are edges here. And these are the nodes. So in order to compute the number of edges, since we are talking about the fully connected network, such as a normal neural network, so we have to do a summation from L0 up to L minus 1 of all the D's of that layer plus 1 multiplied at D. So suppose you have 3 by 3, just like the figure that I had. So you can easily compute how many neurons you want, right? So it's simply a multiplication of this and that. And you have to sum them up for all the layers. Okay? So in total, if you do a rough estimation, you're going to see that the Q is overwhelmingly larger than V, because you have many edges and a high number of nodes. So if you go towards higher order of networks, so you can simply disregard this and just count it as a number of Qs here, right? In a higher order. All right. As before, let's see how we're going to calculate the loss function. It's going to be pretty straightforward again, just before. So we use the square error in this case. So the g x of L of y, x of L and y is going to be your x of L that you calculated minus y, which was the true label, and we squared 2. So it's going to be the squared error of the loss function. And for the classification case, as before, let's have the omega as your model parameters. So all the weights, W1 up to WL. Oh, sorry. I'm not sure why the next one doesn't show up. Let me see. Ah, crazy PowerPoint. So yeah, after that, you have to calculate the En of omega, right? For all your model parameters. And this is going to be the loss function applied to that example. The xn and the output of that, which was y, right? So now, after we finish one pass, so as if we start by putting their input, and we do all the summation and calculations like for the nodes, and then applying the so this is another layer node, and this is the activation function. So after you do that for many hidden layers, you're going to have the output, right? So now, given this output in a training phase, just like before, we have to use the information we got here, and then so you should compare this to the true y. So after you computed this, you're going to use again the stochastic gradient descent or the traditional gradient descent, and then it's going to give you the direction and the correct step size to go towards your local minima, right? Now we have to see how we're going to update all those weights coming back after your forward pass, right? So this is a forward pass. Now we by using gradient descent, we see that our calculated or our estimated weight was, say, 95, right? And we see the correct label, and a weight of that was maybe 91, right? So using gradient descent, it's going to give you that your gradient is almost this, and you have to find a direction in order to go towards your local minimum, right? So maybe you were here, you need to go towards here for your next step. Now we have to have another pass, which we call backward pass, and use this gradient to update all the individual nodes of each layer backward through the network, right? So first, let's see how we're going to find the gradient. As you knew already, so we're going to use the stochastic gradient descent. So in the iteration number k, we have to do the following. We have to select xn and yn at random because it's stochastic. And just like before, suppose your omega k was representing your parameters. And then you're going to apply the forward pass to compute that loss function. And then SGD, using the derivatives and Taylor series and all those things that we already discussed, we can compute this for every I and j of L, right? So this corresponds to dE of n of omega k divided by Wj of L. And now we have to update the weight Wij of L. We're going to update it by our step size and the specific gradient that we got out of those derivations. Okay, now, so how will we compute this? So as if in your network, so this is going to represent your node I on the previous layer, layer L-1, and this is your current layer, node N. So suppose you have many of these, and that was your output. You compute the loss function here. And then this yields to a W, to a delta W that needs to be adjusted to your weight W, I, and J, right? So just like the example that I had, like suppose this was 91, and this showed that you have to adjust it by maybe this amount. Okay. So we simply replace Wij of L by the delta W. We adjust it with that, keeping all the other weights fixed at this point. So now, let a new omega we have, because we have adjusted the weights, right? We don't talk about the previous W's. So we can define the omega plus of K as a resulting model. So with the new weights, and then we're gonna have this equal to, as if you do that, En omega plus K minus En the previous omega with the previous weights divided by the delta that we found by the gradient. So we need to repeat this for all of those weights, right? Wi, I and J in the layer L. So now, as you see, adjusting all the weights for all our W's seems like a cumbersome problem, right? Because you have to do it for all of those Q's you had. So let's see what's the complexity of gradient descent in this case. So now, it turns out that the total number of computations you have to do in order to compute that is going to be the order of Q squared. And this is going to be a huge number because Q was the all of your edges, and it was already a very large number, right? So you see that why for many years neural networks was like there, but nobody was able to utilize it in the 70s and 80s, and those eras which we didn't have any GPUs to the extent that we have today, or accelerators or multi-cores or any other thing. That's why the neural network was going in a very slow pace, right? Because for one round of forward and backward pass, you have to update all of those weights, and the order was very, very large. So one of the very reasons people couldn't expand their networks and they were limited to like a multiple layers, like 2 or 3, was because of this. But later on, in the late 80s, so suppose if your Q was 10 millions, so the order would be a significantly large number, which is unacceptable if you want to iteratively do that for like 10,000 times when you want to train your model, right? So it's going to be a huge number. So up until 1986, which Jeffrey Hinton and Rommel Hart and his collaborators, so they devised a backprop algorithm that required only an order of OQ, and this was a huge improvement, and that was one of the foundation of neural network that still could be able to carry on. All right. If you wanted to have a look, I'll mention the paper in the next slide. But basically, we're gonna learn what the backprop proposed by Hinton and his collaborators are in the next session. All right. So that was the paper if you wanted to have a reference. So learning internal representation by error propagation. If you check Google Scholar, this paper has maybe more than 30K citations by now. All right. So let's see what exactly we need to calculate. So your weights and x's are coming from layer L minus 1, and you do the calculation with this too. You compute the S of J of L, J of L here, and then you apply the activation function, and then it's going to pass it to the next layer, right, as J of L. So now, when we found using the softmax or any of the things at the very end, when we found the gradient, so we want to come back and calculate this amount. For every node J we had. So let's start seeing what exactly this is. Okay, so you had your loss function as derivative of En of omega divided by dWij of L, so which is equivalent to this value, dEn omega divided by the S of L of L, S of J of L multiplied by the S of J of L, as a denominator we have the weights, the delta of the weights. So it's like the same, you can just cross these two together, right? And then we start this. Right. So now let our delta J of L be dEn of omega and ds of J of L. So specifically this value that we wanted to compute here, right? Here. Oh, actually, no, not this one. It's the other one here. So that's this, right? So let this delta be equal to that. Thus, we're going to have delta Sj of L divided by dW ij of L. If you divide these two, you're going to find the input of the previous layer, right? Because using the input of the previous layer multiplied by the W's, you would compute S of J, right? So it's the other way around. And if you recall, we would compute this like two sessions ago. Sj of L was equal to W0 of J in the layer L plus the summation of from M1 up to DL minus 1 of all those inputs, X's and the W's, right? So now using these two, we can have our dEn omega divided by dWij of L is xi L minus 1 multiply the delta J L, right? Okay, now so we need to compute this for all the i's in a span of d plus 1 from 0 to d plus 1 of, this is L minus 1, this I, and also j's in a span of 1 up to dl. So using the formula we found in the previous slide, so this is as if you have to compute this. So the gradient associated with each of those w's in the layers is equal to xi L minus 1 multiplied by this value delta L transpose in a vector space. So we have everything except this delta, right? We have the x's, we have the w's, we have the delta en because we found the loss function, and we had those w, I, and j's in the previous iteration. So what we need to calculate in each of the backward paths was a value which was unknown, and we call it delta here. So in a vector space, so your xi L minus 1, you could represent it as this vector, x0 L minus 1, x1 L minus 1 up to xt L minus 1 of L minus 1. And then this vector would have some values as delta 1 of L up to delta L, delta D of L in a layer L, right? So if you put them all together in a vector space. So this value was basically what we need to compute. So delta L. And that's exactly what's going to be the topic of your next session when we talk about the backprop algorithm. So starting from the last layer, we have to compute this going backward for each of the nodes and update the weights based on that. Okay? I could have started backprop right now, but I thought let's just have a fresh start on Monday. So any questions so far? Okay. So yeah, you can get some rest this weekend because on Monday we have a long session. Okay. So I'm going to conclude maybe now.